So let's look a little more closely at this concept of gravitational field. As I said, gravitational field it's a very abstract idea. It's very intangible, whereas I can see objects and I can touch objects. I cannot touch the gravitational field of an object. It's something that I experience. The gravitational field exerts a force on me, but I cannot feel the force in the sense of the way I feel contact forces. And in fact, the gravitational field can exert a force on me and I would not necessarily be aware of it. For example, if we are in free fall, the gravitational force is still in contact. I still feel that force. I shouldn't say it's in contact, but I still feel the force, but yet I don't have any perception that that force is acting on me, because I only become aware of the gravitational field when that gravitational field pulls me towards something and I feel the return force. I feel the normal force typically. Or I could be hanging on a rope and I feel the rope pulling up on me. Normally I don't feel the gravitational field unless something else, some other contact force, reveals to me that there is a gravitational field. For example, the astronauts. The astronauts feel gravity where they are, but they don't perceive it because, of course, they're in motion. They're essentially in constant free fall. So the definition of the gravitational field is, in essence, an invisible substance. It is an object in the sense that there is something there, but it's not an object like mass. It's not like an object like the things that you typically think about in your everyday life. It's an invisible substance that carries the gravitational force, that allows the gravitational force to be felt at a distance even when two objects are not in contact with each other. Now we have kind of a convention for how we describe the gravitational field, and that is that we use something called field lines. And this is it's like a visualization tool. They really don't exist. Field lines do not exist. So think carefully what I'm saying. The gravitational field, of course it does exist. It's a real object. It's not something that you can feel or sense or perceive necessarily, but it is a real object. The field lines that I'm about to draw, these are not real objects. These are simply a tool to help us try to envision what the gravitational field looks like surrounding an object. So, for example, since we're talking about being off of a planet, I could draw the surface of a planet, and we imagine the field lines as pointing in directly in towards the center of the planet. And in fact, they actually continue inside the planet field lines. The way we would describe this is they point radially towards the mass. So field lines point towards the mass. Now we have this sort of concept, and this is not something that I would test you on. You're not asked for this in the syllabus, but we sort of think of the gravitational field strength. One way of thinking about it is, if you notice that, for example, if I draw in a few more gravitational field lines, let's draw in a few here extra. So if you can imagine that I took a little loop of space like this, and you'll notice that 4 lines go through that field, that little loop of space, that little area, sort of a little flat area with field lines that are pointing down into that point. There are 4 of them. But now if I take that same loop and I move it up here a little farther away, same size loop, but now it only captures 2 lines. You can imagine that if I went farther away, I would eventually only capture 1 line, or half of a line, or a third of a line. So the number of lines that pass through a point and in this case we're talking about an area this is called the flux. Again, you're not going to be tested on it. It's something that you'll see, we'll talk about again when we get to the next invisible field, which will be electricity and magnetism. We can have gravitational flux, I can have electric flux, I can have magnetic flux. It's essentially the number of these imaginary lines that pass through a certain point, and the flux gets weaker. That is to say, there's a smaller number of lines as you move farther away from the object. So the gravitational flux is simply the number of imaginary lines passing through a given area, and in this case the given area is 1 square meter. Now, what happens if we look at just a little teeny piece of the Earth like this? Well, as you might recognize, if we look at the Earth on a very small scale, the Earth appears to be perfectly flat. And so in this case, we end up with what we would refer to as a uniform gravitational field. Is the field technically perfectly uniform? No. Technically, these lines do radiate away from each other. They actually are bending away from each other slightly. But on a very small scale, that's imperceptible. So this is what we would refer to as a uniform. And typically, most objects are small enough that we can take them to have uniform gravitational fields at their surfaces. So at the surface of the Earth, or the surface of the Moon, or the Sun, or Jupiter, or moons, typically most objects have very uniform gravitational field lines. An example of an object that would not ever have uniform gravitational field lines would be you. For example, you do not have uniform gravitational field lines because you're relatively small, and the curvature of your mass is pretty sharp. Whereas, as you can tell from being on the surface of the Earth, the curvature of the Earth is relatively small in comparison to, say, a couple of meters or even a couple of miles. The Earth is fairly flat over that small distance.